let's work with that data set, which is called the morphometrics data set. And of course, I'm not going to type out morphometrics every time we do this. So I'm just going to call it MM. And this is a real data set from a Stat 50/50 class a couple of years ago, and measured mass and forearm and bicep and chest and neck and all these different measurements. And the question is, can we try to predict your mass? So let's start by doing a plot of this data set. I'm going to make my window a little bigger because this is a matrix plot with all these variables. It shows you the plot of mass by forearm, mass by bicep, forearm by bicep. Forearm by bicep is also here. That's why these two are mirror images. Bicep by chest. Now, if we're predicting mass, these plots right here are the ones that we're most interested in. The problem is, because we've done so many of these plots, you really can't see anything in here. But there is one subtlety that you can see. Notice, for example, the plot between bicep and chest. Now, our goal isn't to predict chest or bicep, it's to predict mass. But if you look at the plot of chest by bicep, can you see how there's a relationship here? If I know your chest circumference measurement, I also have a pretty good idea of guessing your bicep measurement. Or also, if we looked at forearm by bicep, that one has a decent linear relationship. If I measure your forearm, I can take a good guess at your bicep. So do I need both those variables in the model? Possibly not. This matrix plot gives us a hint that there's some multi-collinearity going on here, and because of that collinearity, we're not going to need every variable. So let's start with a model where we just throw all these variables in hang on. So let's start with a model where we just throw all these variables in, and let's take a look at our residuals. Do I see any patterns here? Not a strong one. The QQ plot looks good. It's following the line. Randomness here. There's a few data points that seem to be strongly influential, but not overly strongly. I think this is a good model, and that's why we're going to start with this data set, is it doesn't have complicated stuff. There's no squaring and there's no interactions, at least not ones that we can see with this data. So now let's look at our model and see if we can make it any shorter. We have here a ton of variables. We don't care about the intercept. It just needs to be there so that we have a good predictable model. And forearms may be significant. Waist is definitely significant. Height looks like it could be significant, and nothing else. So if you only use this output to make your decision, you would say waist and height are the only things we need. But because of multicollinearity, we're not just going to blindly say that. Who's got the biggest p-value? This guy right here, 0.9. So let's take out shoulder. With shoulder gone, we have a little bit smaller output, and waist is still definitely significant, so is height. But now forearm has popped up. Hey, me too, on this group project if I have to. Now, who else should we take out? We're clearly not done. I mean, look at some of these big p-values. Bicep, looks like that one's got the biggest p-value, so now we have a smaller model. And look at head. Head's about to become significant. Hey, count me in. I'm useful. If you want to tell someone's mass, you need to measure their head. Who are we going to take out next? It looks like neck here. Apparently, measuring someone's neck is not the right way to figure out their mass. Okay, forearm is definitely significant. Head is still borderline. We can make our model a little shorter. Let's try chest. With chest gone, forearm, waist, and height, we've had those the whole time. Head actually has gone up now, and look, thigh is now going down. We do have calf, which is pretty good, with a high p-value, so let's get rid of calf next. And thigh has definitely rocketed up and said, hey, if you want to know how heavy mass is size, right? How big someone is, measuring their thigh helps, and head is like, yeah, no. See, at one point, we thought head might be in the model, and then that p-value went back up. Whatever head measurement is useful, it looks like if you measure the thigh, you can get that same value, which I would love to have a physiologist explain why. Let's look. We have all nice p-values, and it should be that we haven't messed up the residuals because we only took out things with a large p-value. And yep, still looks good. So in fact, look at that leverage plot. It actually looks a little bit better once we've cleared out looking at patterns that don't really exist. Some of those dots that seemed a little strange don't seem as strange anymore. So I'm ready to declare that I have my final model. If you want to measure someone's mass, you get their forearm, waist, height, and thigh measurement, which those are all big indicators of how big someone is. If you go to those carnivals where they try to guess your height and weight, these are the things they look at. Now, in the report, do I need to mention all these other variables? The answer is yes, you should mention shoulder because the client's going to wonder, why aren't you talking about shoulder in measuring someone's mass? All you have to say is, shoulder was not kept in the model, it had a large p-value, or something to that effect, and then you don't need to discuss the effect of shoulder on mass because the other variables that are left are going to do it. Weight and forearm and height are going to explain what shoulder could have done. But was this the only answer? Let's start over here with the full model, and we're going to use a different rule to decide what to delete. Now, before we cut shoulder, but let's say shoulder is easy to measure, but thigh is not. Thigh makes me uncomfortable. I don't want to measure someone's thigh. I mean, try doing that without it being awkward. So I'm going to delete thigh. Can I get away with that? Well, thigh is not significant. So yes, it's okay to choose thigh to go if you have some good reason. Now, if you've chosen a smaller p-value in favor of a larger p-value, there should be a justification. And in this case, the justification is I don't know how to measure someone's thigh without it being creepy. So we're going to take thigh out. This is going to force us to get a different model because last time thigh was one of the variables that ended up surviving. And look, here we have head now pops up, height and waist are still there, and forearm is still there. Okay, what should we take out next? I'm going to choose chest because I'm trying to imagine measuring a random person's chest, and half the time I think it'd be fine, and the other half of the time it's fantastic. So there we've taken out chest, and look at that, head popped back out for a second there. I really thought that it was going to make it to the end. So among these variables that are left, are there any that are really uncomfortable to measure? I'm going to claim cat. Not that it's necessarily weird, but just because that's close to feet, and I think it sounds smelly. So we're going to take out calf. How's it looking? So you have a little bit of a dilemma. I think it's uncomfortable to measure waist, but waist is so very significant that I'm hesitant to take it out. There actually could be a justification for it. I worry that we might get less of a model. And shoulder is so definitely not significant that I feel like to leave it in, you would really have to have a strong statement on how shoulder is easy or desirable to measure something. What do we have left here? Well, head's easy to measure. We'll say neck is easy to measure. How about bicep? I'm purposely just jumping around, not picking the largest p-value. So we'll claim bicep, and we'll give it some weird psychological reason. Who cares? What do we have left? Okay, neck and head. And I think it would be cool if head survived, so I'm going to try neck. And is head going to finally... Nope, nope. Head says, look, there's nothing here. You're fishing for patterns. Which leaves us with only 3 terms. The model we had before had 4 terms, but because we went out of order, this is what we had. Just to emphasize this point, let's try it one last time. And this time we're going to delete waist. Now, waist was definitely the highest p-value, so deleting it's kind of like, how could you do that? Well, let's pretend that there was some reason why waist was really not desirable to be able to measure. And so the client says, I really don't want that in the model. Okay, if that's what you don't want, let's see how good our model can get. Look at that. Nothing is useful. Well, hold on. Let's see what we can get. Bicep has the biggest p-value now. So there. And then chest. You can see how hard it is to fit this data well because these are all terms that used to be very important. And as we shrink our model down, it's getting harder and harder to find something. Thigh is trying, but apparently these measurements don't make it easy to get your mass. Okay, so the thigh definitely does help, but I'm not convinced we're going to like what we end up with here. We're down to only 3 variables. Woo! And bam! All of a sudden, all 3 of those variables, yes, we will help predict the mass. Now, because we deleted such a highly significant variable, I think it's justifiable to say I need to look at those residual plots. Yeah, I kind of see a little bit of swerve here. The QQ plot still looks good. I don't know that there's any data points that are necessarily a huge issue. So maybe the residual plots are less desirable. So far in this video, we've seen 4 different models. The full model, where we had everything and didn't take anything out. And then we walked through it backwards, taking out stuff that wasn't significant, and ended up with this model. And then we did it differently, where we said, I want only the variables I'm comfortable measuring. We only took out variables with large p-values, but among all the variables with large p-values, we took out the ones that we weren't comfortable measuring. And then we did one where we specifically took out waste to see what that would do. So I went back and looked at all 4 of these models. I found the r squared, the s, that r squared adjusted, and let's make a little list of the benefits. So for the full model, here's our highest r squared, and that's always going to be true. The model that has the most variables has the highest r squared. Usually it'll have the smallest s, but in this case, actually going with the method that we've been talking about, you actually get a smaller s, which is unusual, pretty cool. I think this model here has a lot going for it. It follows the rules the way we said. Now, this model doesn't have quite as good an r squared, but we don't really look at that. The r squared adjusted is a little drop. That's meaningful. It's not quite as good a model, but it's awful close. And it avoids the variables that we said were hard to measure. If we got rid of waste, there is a drop. Look at the r squared adjusted, 94 to 87. We've definitely lost something. Our standard error from 2.4 to 3.9, we don't have as good an accuracy. But if you really, really wanted to get rid of waste, well, then this is probably the best model you could use. So you could justify any of these models. What model would I expect you to use? Probably this one with the backwards model selection. It follows the method that we've been talking about, and I think it's what most students would use. Now, in the next video, let's look at some more examples and see some stuff that's a little more complicated.